afternoon, everyone. So today we'll be solving some questions related to week 9 content of control engineering course, and the content is related to compensator design in frequency domain for this closed loop system. So we'll proceed with the questions. Now, I believe that you all have gone through the lectures, and in the lectures in this week, the different compensators like lead lag that we have last time we did it in time domain, design of lead lag or lead lag compensator in time domain. This time we'll be doing this in frequency domain design of this lead compensator, lag compensator, and lead lag compensator. And we had seen in last last problem solving session that this compensator is used basically for improving the transient response of the closed loop system. And once the transient response is achieved, then if there is this steady state response that is required to be satisfied by the control loop, the closed loop system, then lag compensator is used. This is used for steady state, can say performance. And then we had seen that if there is some, when there is this transient response has to be satisfied, then in that case this lead lag compensator is used. And the design procedure was such that we had this open loop system, open loop transfer function, and then this is the reference, this is the compensator GC. So it was the design process is such that first it is assumed that GC is a constant, so simply a gain, and gain is varied such that the desired performance is achieved or not, it is checked by varying this gain. Now, if the root, while varying the gain, the roots on the root locus doesn't pass through the desired poles, then it is said that okay, the performance lag compensator based on what performance requirement is given by the designer. Now, in the frequency response, we again can do the same thing. We can design the compensator, but the procedure is little different. So we'll see how to do that. Now, the main thing is that it is considered that the closed loop system has a dominant poles and it is of second order. So consider dominant poles. Now, in order to modify, it was seen that if there is this border plot, then there were three regions in the frequency. So in this region, low frequency region, it is said that this is one region where this steady state behavior is determined by this region, and then transient behavior of the system depends on the border plot in this region, second region, and in this region, this is a high frequency region. Basically, here the loop gain should be very low so that noise is attenuated, because noise are generally high frequency signal. So this was the thing. Now we'll go through, since you have we have gone through the concept, we'll start solving the question. So a group of control engineering student is attempted to control a plant GS. So this is GS, shown in figure below. Now the system has a controller GC, but the group is unable to select GC appropriately. So this is a compensator design problem. It is agreed that a system with phase margin 50 degree is acceptable. Okay. So what is the phase margin? Phase margin would be approximately 50 degree. Okay. So that has to be achieved. Now for this, first what we do, we see what is the phase margin of this system. So we have GS, or we can say this is GS, this is S plus 10. Now we have to find the phase margin of this system. So it says what is the phase margin of the plant? Plant is GS. So we know for phase margin, if we have this kind of Nyquist plot, suppose. And this is imaginary part of GS. So phase margin will be such that frequency at which the gain of the system is 1. So if suppose this is omega equal to omega GC, gain crossover frequency. So G of more means magnitude of G at omega equal to omega GC will be 1. And at this frequency, whatever phase that has to be applied such that phase shift that is required so that this system tends to verge of instability, that would be the phase margin. So we have this one at gain crossover frequency, magnitude of this transfer function of the plant will be equal to 1. So we'll just equate this. This is 10 j omega plus 10. This one is equal to 1. Now this would be 10 by omega equal to omega GC. Omega GC, omega GC square plus 100 is equal to 1. Now, if we try to equate this one, this would be 100 equal to omega GC square, omega GC square plus 100. So this, let us consider T equal to omega GC square. So now we can solve this, will become a quadratic equation. And this would be T plus 100 equal to 100. And if we solve this, the solution is like T equal to 0.9902. Now, since we find T, we can say what is, so this implies omega GC is equal to root under 0.9902. This would be 0.995 radian per second. So this is the frequency or grain crossover frequency. So at this frequency, this magnitude of the this plant transfer function is 1. So now we know this. You can see the loop gain is 1. Loop transfer function. So we have this frequency, this gain crossover frequency. Now we need to find the phase margin. So for this, just apply the formula of phase margin. This would be 180 plus angle of G. omega equal to omega GC. So this will be 180. And what would be the angle contributed by, phase angle contributed by G of j omega? This will be 90 degree because of this, and tan inverse omega by 10. So minus 90 degree due to one pole at 0, and minus tan inverse omega GC by 10. Okay. So we have this 90 minus tan inverse omega GC, what it is, 0.995 by 10. And this gives us 84.32 degree. So this is the phase margin of this plant, GS. So let us see if we can find it through from MATLAB also, CLC. This is the plant G, and we have this transfer function, which is 10 by S plus 10. So this is 10, comma, S plus S into S plus 10. So this is S squared plus 10S. So 1 S squared plus 10S plus 0. This is the transfer function. Now we see the border plot of this one. The border plot. Let's maximize this. So what is the phase margin? We can see here it's 84.3 degree. And what is the frequency, or like gain crossover frequency? This is 0.995 as we have calculated theoretically. Okay. So this much we know. We know the, since the phase margin is this much and gain margin is infinity. So we know that this system is a stable system. This closed loop system is stable. Okay, so let us proceed. The group decide to choose GC equal to K. So now there is this gain K, and find the value of K that yields phase margin of 50 degree. So we had this G, which was 10 by S plus S plus 10. This is the gain K. This unity feedback. This is the overall closed loop system, and it says that the phase margin of this system should be this system is such that this phase margin of this open loop transfer function is 50 degree. So now we have GC equal to K, and what is the open loop transfer function? This is G into GC. H is 1 because this is unity. So this would be 10 K by S plus 10. Okay. So this much we know. Now what is the phase margin? Phase margin is 50 degree for this one. So that means, and this phase margin is 180 degree plus angle of GGC. So this implies 180 minus 90 minus tan inverse omega by 10 is equal to 50 degree. Now we'll just equate this. So we have tan inverse omega by 10 equal to 40 degree, and this gives omega equal to 8.391 radian per second. So this is the frequency at which phase margin is 50 degree. If okay, now at this frequency, what is expected? This should be, because at this frequency phase margin is, if we consider this frequency, phase margin is 50 degree. Yes, the angle is 50 degree, and this should be our phase margin. So at this point, this angle or magnitude of G into GC should be 1. So this means 10K by omega root under 100 plus omega square at omega equal to 8.391 is equal to 1. Now we'll just solve it. So what would it be? This would be K equal to 8.39. This will be root under 100 plus 8.39 whole square. This by 10. So this would give us 8.39 into 13.054 by 10. This is equal to 10.954. So this is the value of K, and if K is chosen this one, then the phase margin becomes 50 degree, and the frequency, this gain over crossover frequency, so at this gain the phase margin becomes 50 degree, and the frequency at which this is happening, or we can say gain crossover frequency, is 8.391 radian per second. So let us see if we can find it through MATLAB also. So now we had this G, which was the transfer function, and we have this compensator, which is simply a gain, and gain value we have found out, which is, what is the gain value? 10.954. 10.954. Okay. See the border plot. This orange one is the new plot, a new border plot. So we can see, we know, like when we are multiplying gain in open loop transfer function, the phase plot remains as it is, because there is no contribution in phase angle because of gain, and the magnitude plot is shifted upwards with increase in gain. So here, let us see what is the phase margin. Phase margin is 50 degree and the frequency is 8.39 degree. So this is the what we have obtained, like, through calculation. So this is fine. Now let us proceed to next part of the question. So it is asking, what is the settling time in seconds in the step response of system for value of K obtained in question 2. So the system was, when there was no gain, the system was simply G with feedback, simple feedback. And this was the overall closed loop system. No? So for this closed loop system, we can see what is the step response. Let us a figure window, and then we'll have a step. It shows the step response of the feedback system. So feedback with forward transfer function G, and flow back, like feedback is unity. We'll have this step. So this is the step response. We can see it is taking approximately 4.5 or 4 seconds to reach the reference, which is the step. So unit step. Okay, this is for system without this gain compensator. So now we'll see what is the response when this gain is there in the as compensator. So hold on, this will be multiplied by 10.954. Let's see what is the response. So we can see the orange one is the response when there is this gain in the forward path, and here we can see the settling time has decreased. Okay, and there is this overshoot which is occurring. So we'll just try to find what is the value of settling time. From here also we can find it. Approximately 0.787. And for the uncompensated system, it was 3.59. Okay, let us find it out. So it is asking for the value of K obtained, what is the settling time. So for settling time, we can see what is the closed loop transfer function. So suppose this is Y, this is R. So we can find the closed loop transfer function. Now we have this gain K. So this will be Kg. And this G is 10 by S plus 10. Here we have 10 by 10K by S plus 10. So what is the closed loop transfer function? This is simply 10K S square plus 10S plus 10K. Now this is the closed loop transfer function when there is this gain K. So the value of K we know, and we have to find what is the settling time. So this is a kind of second order system. So Ts will be 4 by zeta omega n. Now we'll try to find this one. So from here, what is a standard second order system transfer function? Omega n squared by s squared plus 2 zeta omega n s plus omega n squared. So we know 2 zeta omega n is equal to 10 from here. If we equate these two, so zeta omega n is equal to 5, and we have 4 by 5. So this is 0.8 second. Now what we have got, this is 0.787. So approximately this much is the settling time. Okay. So from here, what we have seen that for uncompensated system, we found that the phase margin is high, system is stable. Now we are just trying to obtain a phase margin of 50 degree. So what we have done, we have tried to see if adjusting the gain in the forward path can help. So we have tried to find out the value of gain, and we say that okay, at this value of gain, that is 10.954, we can have this gain phase margin which is 50 degree. So this we have seen. But apart from this, we can also observe that with increasing, when we are increasing this one, there is this decrease in settling time we are observing. So it is approximately 0.8 seconds. Now let us proceed to next part of this question. So the group further decide to use a compensator of form GC equal to T S plus 10 S plus 20. So this is a compensator that is being used. Now if you see this compensator, so this has 0 at -10 and pole at -20. So it's kind of a lead compensator. So this will help in improving the transient response. So basically it will try to decrease the peak overshoot, also decrease the settling time. This we can using lead compensator will have these kind of effect. So this is the lead, compensator that is being used to reduce the settling time. Determine the gain T that result in a phase margin of 50 degrees. So with same phase margin, and now this has to be achieved. That settling time has to reduce. So that means what? We have this phase plot. So phase margin has to be same. Now in this case, when lead compensator is being used, it's like this, -180 degree. Okay. Now when lead compensator is being used, so at higher frequency, what it does, it adds positive phase. So in that case, this becomes some kind of this one. And because of this, this bandwidth is increasing, and also this phase margin frequency will shift towards right. Okay, so this will observe. Now it is said what is the gain of gain T that result in phase margin 50 degree. So what was in that case? What do we want? The phase margin should be 50 degree and we want to find the gain. So now the closed loop system is 10 by S plus 10. And we have this GC, which is T S plus 10 by S plus 20. This will, we can say what is the open loop transfer function. This will be G into GC because H is unity. So you can ignore this. 10T by S plus 10 into S plus 10 by S plus 20. These two will cancel out. So 10T by S plus 20. This is the open loop transfer function. Now phase margin is 50 degree. So we have 180 degree plus angle contributed by GGC is equal to 50 degree. This would be 180 degree minus 90 minus tan inverse omega by 20 because of this and this one. So this would be 40 degree equal to tan inverse omega by 20. We'll just solve it. We'll get omega equal to 16.78 radian per second. So this is the frequency at which phase margin is 50 degree. Now to have this phase margin 50 degree at this frequency, the magnitude of this open loop transfer function should be 1. 0.78. So this should give root under 400 plus omega square. Omega equal to 16.78. By 1. So this should give 400 plus 16.7 whole square. This would be 16.78 into 26.11 by 10. So this is the gain. Let us see if we get this one or not. So what is the open loop transfer function? We have this GC, which is TF S plus 10 and S plus 20. Now we have to find the border plot of the magnitude is 43.81 star G star GC. Yes, multiplied by GC. So what we get this yellow plot. I hope this is visible. So earlier, this was the phase margin for uncompensated system. Then we had increased the gain and the simple gain. And we found that, okay, we can have phase margin at this frequency. Now we have included this lead compensator and we want same phase margin. So this we get the border plot that we get with lead compensator is this one. This has phase margin 50 and the frequency at which it is achieved is this 16.8 radian per second. So here from magnitude plot also we can say that bandwidth has increased for system. So what we expect for when we are using lead compensator, that compared to this one, this red one, which is with the simple gain, and this closed loop system with compensator will have faster response. So settling time will be less. Earlier we found that settling time for compensator system with gain was 0.787, so 0.8 seconds. So now we'll find what is the settling time for the compensator system with lead compensator. So for this one, we can find the closed loop transfer function for this system, compensated one. So what we get, this is the open loop transfer function. We'll have 10t by ss plus 10. 20 or 10. By 1 plus 10t by s plus 20. This is y. So this gives 10t s square plus 20s plus 10t. Now again, we'll just equate this with a standard second order system. So what do we get? Ts is equal to 4 by zeta omega n. Now 2 zeta omega n is equal to 20. So zeta omega n is equal to 10. This implies 4 by 10 and 0.4 seconds. Earlier what we had, it was 0.8 seconds. Now it is supposed to be 0.4 seconds. So let us see if we get this. So we'll have the step response. We'll try to find out. Just hold on. A step feedback system with forward path, which is this one. comma, unity feedback. So I hope this is visible. This is the yellow plot, which is corresponding to compensator system. And here we can see what is the settling time. It's 0.393. So obviously response is faster. And this is how we are achieving this lesser sampling time using compensator and gain. This is about the lead compensator. So obviously we have seen how this is improving the transient response. Now let us proceed to next question. So consider the following open loop transfer function. G is equal to K by S 2S plus 1 and 5S plus 1. Okay. It is desired that lag compensated system meets the following specification. So what is the, so this is GS, and we have a compensator, G lag is a unity feedback system. Fine. It is this one. What is expected? AV should be 0.5 and phase margin should be 40 degree. This is a desired behavior. Okay. So what is said? The gain K required to meet a steady state specification KB. So obviously when we have this lag compensator, what is this one? This will be J omega T plus 1 by J omega beta T plus 1, where beta is greater than 1. And what we expect, that this lag compensator will have this attenuating behavior. This is the magnitude of this GC, or we can say G lag with frequency. And with frequency, this is the phase shift. So this phase shift is negative phase shift. So basically it causes the slower the response of the compensator system. And here we can see this 0 dB line. So it is passing the lower frequency without changing it, but for with increasing frequency, attenuation increases. It rejects noise basically. Okay. So first we have to see what is the gain K so that KV specification is met. So first we have to change gain. Suppose this G lag is gain K, and this K into K dash will be some K double dash. So basically we have to overall gain we have to change. So what would be KV? KV is simply one more thing. Since it is saying a specification in terms in velocity error constant, why not in like simple step error constant? So we have this as integrator. We can say integrator dynamics in forward path. So if we apply this unit step, it will always be followed. It will always be tracked. But if we apply ramp, it has this dynamics of 1 by s squared, and the in forward path, since there is only one integrator, that would not be able to track this dynamics. Therefore, we are talking about this velocity error constant. Now, this is simply limit s tending to 0 as GS. So just equate it. What do we get? Limit s tending to 0 as K by S 2S plus 1 and 5S plus 1. and this would be equal to 0.5. So this is what? This SS cancels out. This is K equal to 0.5. Now for this K, this system has for this gain, the steady state error specification is satisfied. Okay, once the steady state error specification is satisfied, now let us see. We'll move further and see what is the next part of this question. So, the gain crossover frequency of gain adjusted system. So we had this system, now we have this gain adjusted system. Let us see what we find through MATLAB. So we have this system k by s, 2s plus 1, 5s plus 1. Suppose we'll try to find the denominator. So this will be convolution of 2s plus 1, then 5s plus 1. These are two terms, and apart from this, there is this integrator. So let us first find this. So this is 1. And now we'll again convolve this with integrator. So this would be 1, 0, comma, answer. So this is the overall coefficient in denominator. Now, what is G? G is transfer function with numerator, that is 0.5, and denominator, which is this answer. So this is the overall transfer function, open loop transfer function basically, and we'll have a Bode plot for this one. Let us see what are the. So what is the phase margin? It is 9.1 degree at frequency 0.266. And error constant from here we can try to find out. Basically use a formula and all. So here we can see when we have this uncompensated system. And for this uncompensated system, we had to find gain K such that with this gain, this satisfies this steady state specification that K be equal to 0.5. Now, once this is satisfied, we can see this phase margin is very small, 9.0. So it is like relatively not that much stable. And this is at low frequency region, because here this is 0.1 radian per second, then this is 1 radian per second. So at low frequency region, we can say that this is a phase margin and it is not that much large. Gain margin is positive, phase margin also positive. So system is stable, but relatively it's not that stable. Okay. So what we have to do, we have to increase the phase margin by 40 degree, because this is the specification, this 40 degree. And as of now, the phase margin is 9.01 degree. Okay. So let's start with this design. So for designing this one, what we do, what is required? We'll have to add this 40 degree. I mean, this, since this is 40 degree and this is 9.1 degree, so we'll have to add this 40 minus 9.1 degree at this point, this much. Let us proceed faster. What is the gain crossover frequency? The gain crossover frequency we can find out at this frequency. What is the magnitude of this one? G. Should be 1 at omega equal to gain crossover frequency. And this is simply 0.5 by omega GC 2 omega GC square plus 1. And this is 25 omega GC square plus 1. So this should be equal to 1. Now we'll just equate it. We have this 0.5 equal to omega GC square 4 omega GC square plus 1 25 omega GC square plus 1. Now let us omega GC square equal to T. So we'll have this T 4T plus 1 and then 25T plus 1 is equal to 0.5. So I just solve this equation. If we try to solve this, what we get, this T is equal to 0.07 and omega GC will be root under T. So this will be 0.266 radian per second. So this is the gain crossover frequency. Now for this system with gain adjusted gain adjusted system, is it stable or not? So we have seen from this 4-day plot, obviously this is stable because it has positive gain margin that is 2.92 and positive phase margin. So we can check this also. So we'll just find the angle due to this plant, adjusted gain plant. So this will be minus 90 minus tan inverse. What was it? This was K by S, 2S plus 1 and 5S plus 1. So this will be 2 omega minus tan inverse 5 omega. Now this is at what? This angle contribution. This should be at omega equal to omega GC, which is 0.26 is just now we have found out. So we'll just add this one and we'll find. So this will give minus 171.07 degrees. So this is the phase angle of this plant. So what is the phase margin? Phase margin would be 180 plus angle of this G of j omega. This will be 180 plus, but this will be minus. Be 8.93 degree. This is the phase margin. So this is positive. Now we have to check gain margin also. So we'll just apply the gain margin formula. We'll get gain margin is 2.92 degree. So these are positive. That means this system is stable. Okay, now we need to improve the phase margin. So for that, what is being done? We are trying to use this lag compensator. And we have to find this new gain crossover frequency. So what is the required phase margin? Is 40 degree. That means what is the angle that should be computed by this plant? That should be minus 140 degree because this will be minus 180 plus 40 equal to minus 140 degree. we'll just apply this one. This will be minus 90 minus tan inverse 2 omega minus tan inverse 5 omega. And we'll try to find this omega, for which this is minus 140 degree. You see, this is tan inverse 2 omega plus tan inverse 5 omega equal to 50 degree. This gives us tan inverse 2 omega plus 5 omega by 1 minus 10 omega squared. So this is 7 omega by 1 minus 10 omega squared equal to 1.192. This would be 10 omega squared plus 5.8 omega minus 1 equal to 0. Omega is equal to 0.138 radian per second. So what we want to find the new gain cos over frequency. So at this point, the phase angle should be minus 140. If we see, this is minus 140, and what is the frequency? This is 0.139, so approximately 0.138. So this is the new gain crossover frequency. Now, at this point, what is the gain that we have to see? Because this gain has to pass through, basically at this frequency, this magnitude plot should have 0 dB, or this magnitude should be 1. So that much attenuation has to be provided. Okay. So let us see at 0.139 what is the. This is approximately 9.17. This is a magnitude at this point for this 20 log G. So this is what we are expecting. So what we do, based on magnitude, the new gain crossover, find the value of beta. So we know whatever attenuation that has to be provided by this lag compensator should be this one, minus 9.17. This is the attenuation magnitude. So this 20 plus this is 20 log 1 by beta. This would be equal to minus, we can say 20 log 1 this G. Because we have found it from MATLAB, we'll just see if at omega equal to omega GC, the new frequency that we have found. At this point, what is this? Okay, so for this one, this beta will be equal to GS at omega equal to omega GC. And we'll have beta equal to 0.5 by omega root under 4 omega squared plus 1. And this is 25 omega squared plus 1 with omega equal to omega GC that we have found 1.38. So we'll just replace this omega by 0.138. What we get is 2.8746. So this is the beta in the lag compensator. Now it is said this corner frequency corresponding to 0 is 0.1. So 1 by T, because when we are talking about lag compensator, it's like this. So we have j omega t plus 1 by j omega beta t plus 1, and we had two poles. Sorry, one pole and one zero. This is the pole, this is the 0. It is at 1 by beta t, and this is at 1 by t. So we have been given the corner frequency corresponding to 0, which is 0.1. So 1 by t is equal to 0.1. So t would be 10. So corner frequency corresponding to pole, that is 1 by beta t, and beta we have found out, it is 2.87 into 10. So we'll just multiply this. What we'll get? 2.87 into 10. 0.0370. Radian per second. This is approximately this one. So what is the overall transfer function of this lag compensator? This would be j omega 10 plus 1 by j omega 28.7 plus 1. This is the G lag or GC. What is the overall system? We have this 0.5 S, 2S plus 1, and 5S plus 1. J omega 10 plus 1 by we'll try to find out what is the Bode plot for this system. So we have GC equal to transfer function 10, 1, 10S plus 1, and then 28.7 S 1. So this is GC. And what is G? G is this one. So we want Bode plot of this one. Simply Bode GC into G. So this orange one is this. Earlier this was the phase margin. Now it has improved. It's to 15.1 degree. But what is expected is 40 degree. And that much is not being achieved. We can see because of this decrease in this value, because this lag compensator attenuate the gain. So because of that, it is not achieving that much. phase margin. But for this case, for this analysis, we have just ignored the influence of this attenuation due to lag compensator. So what we can do is that we can try to improve the performance using lead compensator once this is done through lag compensator. So let us just see what is the transient response for these two systems. Okay. Figure. This is a step response of this uncompensated system just with gain modified. So this will be feedback G, comma 1. This is the response. It is oscillatory and has last settling time. Now let us see what happens if we have this compensator system. So this is GC star G. Again, it's oscillatory, but it is taking little less time compared to the earlier one. Now what we can do that we can try to use lead compensator along with this lag compensator in order to improve this one. So we have this 15-degree, and for lead compensator already you have seen that we need to find this phi m and alpha that is required. So the phase margin that is required is like for 15 degrees. So additional 40 minus 15 degree will be required, and that can be used to find the phi m. And from there, we can find the value of alpha because we know the phi m, which is 40 minus 15 degrees. So alpha is known, and once alpha is known, and we know the frequency at which we are talking about. So at this point, we can find the T. From there, we can try to design the lead compensator. So that you can do through that. That step is already there in lecture. That also can be tried. But apart from this, this is a way of doing this, designing the lead compensator and lag compensator. I hope this is clear to you. So basically in this question answer session, we have tried to see how this specification, which is in terms of a steady state error, or we can say this transient response, can be achieved through this frequency response analysis. So we are utilizing this open loop transfer function Bode plot in order to see the response. And we are modifying this in this different region that is there. So there is this low frequency region, medium frequency region, and high frequency region. So when we are talking about improving the low, like steady state to the performance, so we say that we are dealing with this low frequency region, which is this one. And when we say that we are dealing with transient response behavior improvement, then we are talking about this medium frequency region. And after that, for this high frequency region, we say that here we consider that this open loop transfer function gain should be low such that the high frequency signals, which are generally noise, would be attenuated. By this, we have completed this compensator design for closed loop system using time domain analysis, that is root locus, and the frequency domain analysis. Any doubt in these questions? Yes. So exams will be MCQ, no? Like I don't have any idea, but I think if we have gone through lectures, it would be easy. It is not that difficult. If you, because in exams, are you allowed to use MATLAB and all? Then it would become more easy. Because these calculation, once you do by hand and doing this in MATLAB, is a lot easier. Okay, so these questions I think you can ask in forum, like discussion forum. I don't have any like a specific idea about this. Our job is just to help you to understand the concept through questions. So I'm trying to do this. Oh, so basically the main thing in this controller, the control system or like control system engineering course that we are doing, first we went through this system modeling and all, understanding the system. We try to model the system, and once we have modeled the system, we went through different type of analysis of the system, like time domain and frequency domain. We saw that if there is a system given, what would be the transient response or steady state response. In the frequency domain, what would be the response of the system. And once we know that this analysis for a system, then we can say how to modify the system such as to achieve desired performance. In that case, we are talking about different type of controllers, and we saw this PID controller. And in the PID controller, we saw that this integrator and differentiator is like basically differentiator is not physically realizable. Integrator is also very difficult to realize. So we try to approximate these with this integrator with lag compensator and differentiator with lead compensator. And then we modify the root locus such that we have dominant poles. So we just try to approximate the overall system with second order system. For frequency domain analysis also, we try to approximate this overall system with this second order system. So this is the overall idea of doing the whole thing. And from this analysis, since we have dominant pole, we can say the overall system behaves like a second order system approximately, which has the specific uh, poles or complex conjugate poles. So this is the overall idea. Okay, so I think this is clear to you. So if you have any doubt, you can ask. Uh, then we can conclude the session. Okay, thank you. Thank you very much.